All right, today we look at section 9.10. We finished chapter 9, Taylor and Maclaurin series. You remember the other day we talked about Taylor and Maclaurin polynomials? What were Taylor and Maclaurin polynomials? Well, they were polynomials, right? And what did we do with those polynomials? We tried to do the approximation. For example, I think we did some work and we showed that e to the x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial, maybe. That would be the third order Maclaurin polynomial for e to the x. So what's a Maclaurin series? Even better than approximating it. We're going to get the exact value. Instead of having a finite polynomial, we're going to develop a power series. So a Taylor or Maclaurin series is the power series for a function. What's the difference between Taylor and Maclaurin?
Taylor at the C.
Taylor is centered at some value c, where Maclaurin is centered at 0. So if I wanted a Taylor polynomial, I would have like a x minus 1 here, and an x minus 1 squared, and an x minus 1 cubed. So they're really the same thing. A Maclaurin series is just a Taylor series centered at 0.
If they equal, the function doesn't matter where it's centered at? Things before they develop the precise.
It will depend on where it's centered, depending on the radius of convergence. If your series converges for all real numbers, then it won't matter where it's centered. But if your series only converges for a radius of 3, then it does matter where it's centered because you can't go outside of that radius of convergence. So that will make a difference. For many of the Maclaurin series or Taylor series we will develop, they will converge for all real numbers. So it won't matter where we're centered, and so we'll make it easy on ourselves and we'll center it at 0. But for example, no matter how hard we want to, we cannot center ln at 0. Because ln of 0 is undefined. So you can't center ln at 0. You'd have to center ln somewhere else. Usually we center it at 1. Okay, so here's the idea. We're going to have f of x to be some power series. And for convenience, let's just say we center it at 0. Everything I'm about to say would also work if you center it at some value c. This is a0 plus a1x plus a2x squared plus a3x cubed plus, goes on and on and on forever. Bless you. What happens if I take that series and I choose to plug in the number 0? I'm going to get 0 for everything except for a sub 0. I'd get 0 here, 0 there, 0 there, but I would get a sub 0. What if I wanted to take the derivative of that series and plug in 0? I would get a1. How come? Well, what happens when you take the derivative? What's the derivative of a0?
0.
0. What's the derivative of a1x?
A1.
A1. What's the derivative of this one?
2a2.
The important thing is it's going to have an x in it still, isn't it? And this one's going to have a x in it. So when I go to plug in 0, that one's gone. All these are gone because they're all going to be 0. The only thing that's going to survive is a1. Okay. What happens if I plug in 0 to the second derivative? Not a2.
2a2.
2a2. Where did the 2 come from?
Yes.
When I take the derivative once, this one disappears, right? When I take the derivative of twice, this one's going to disappear also. But what happens when I take the derivative of this one twice? I got to bring the 2 down, and then I got to bring the 1 down. So not only am I going to have the a2, I'm also going to have a 2 down in front of it. So that would be a 2a2. How about the third derivative at 0?
6a3.
6a3. Why 6?
3 times 2.
Because I've got to take, with 3 derivatives, these first 3 are all going to disappear. When I take the derivative 3 times, I'm going to bring the 3 down, bring the 2 down, bring the 1 down. So I'm going to have 3 times 2 times 1. That's 6, a sub 3. What about f's fourth derivative? 24, a sub 4. So you're starting to see a pattern here. What's the pattern? It's factorial, because when I take the fourth derivative, I bring the 4 down, the 3 down, the 2 down, the 1 down. 4 times 3 times 2 times 1. So in general, the nth derivative at 0 is going to be n factorial a sub n. All right, so that gives us a pattern here. A sub 0 is f at 0 over 0 factorial. How much is 0 factorial? 0 factorial is defined to be 1 because it makes a whole lot of patterns work that we need to work. Seems weird, but that's the way it's defined. A sub 1 is f prime at 0 divided by 1 factorial. A sub 2 is f double prime at 0 divided by 2 factorial, so on and so forth. A sub 3 is the third derivative at 0 divided by 3 factorial. In general, a sub n is the nth derivative at 0 divided by n factorial. So we have this. The Taylor series for any function f of x centered at 0 is f of x as the sum from n equals 0 to infinity of the nth derivative at 0 divided by n factorial x to the n. And if I wish to center it at some other point, I would have f of x is the sum from n equals 0 to infinity of the nth derivative at c, where c is the point where I want to center it, times x minus c to the n. Questions on that?
Which one's the Taylor version from the Taylor?
This one is generally called the Taylor, and centered at 0 is generally called the Maclaurin. So in the book, quite often they will say, determine the Maclaurin polynomial for such and such, or I'm sorry, determine the Maclaurin series for such and such. That's just saying they want it centered at 0. Now you might remember that these coefficients that we ended up with are exactly the same coefficients that we had for the Taylor and the Maclaurin polynomials. So, in essence, a Taylor series or a Maclaurin series is nothing more than an infinite polynomial. All right, so using that information. Oh, one other thing. Are you guaranteed that those will converge? Well, for this one, I'm guaranteed it will converge at x equals c. How do I know it will converge at x equals c?
C minus C is 0.
C minus c is 0. I'd have 0 plus 0 plus 0 plus 0 over and over again. That would be 0. Am I guaranteed it will converge anywhere else? No. So there's a theorem called Taylor's theorem. Taylor's theorem says, if R sub n, which is f at the nth derivative at n plus 1, evaluated at some value z, divided by n plus 1 factorial, times x minus c to the n plus 1, converges to 0 for all n, then the Taylor polynomial converges to the function. As long as the remainder is getting smaller and smaller and smaller, getting closer and closer to 0, you're guaranteed that your series will converge. That's all that's saying. This is the remainder of the Taylor polynomial. So as long as the remainder of your polynomials are getting smaller, when you keep adding terms, your remainder gets smaller and smaller and smaller, gets closer and closer to 0, you're guaranteed that your Taylor series converges to the function. Okay, so for example, find the Maclaurin series for, somebody give me a nice function. Anybody got a function they like a lot?
X squared plus 5x over 7.
F of x equals x squared plus 5x all over 7?
Yeah.
All over 7. Okay. How do I find the Maclaurin series? Well, I start by finding f at 0, f prime at 0, f double prime at 0, f triple prime at 0. Maybe I got to go all the way to the fourth derivative at 0. And I hope that what can happen is that I find a pattern in my values. So let's see if we can find a pattern. Well, the first one's easy. What happens when I take 0 and plug it into my function? I get 0. What's the derivative of x squared plus 5x over 7?
X squared plus 5x plus 2x plus 5 times 7.
What you said might be right. Seems to me as though you did it the hard way, though. What I would do is, instead of dividing by 7, I would write that as 1/7 times x squared plus 5x. And then how do I find the derivative? I don't need the product rule because that 1/7 is just a number. So that 1/7 is just going to stay 2x plus 5. So I plug 0 into that. What do I get when I plug 0 into that? I don't get 0.
5 times
I get 5 over 7, right? Because I plug 0 in, I get 0 plus 5, that's 5, and 5/7. Okay. How about the second derivative? What's the second derivative?
2 sevens.
1/7 times 2. I plug 0 into that, I get 2/7. What's the third derivative?
0.
What's the fourth derivative?
0.
What's the fifth derivative?
0.
So on and so forth forever, right? I like that pattern. I like 0. That's real easy. So, what we just proved, x squared plus 5x over 7 is a sub 0 was 0, plus a sub 1, that's 5 over 7 times x, plus a sub 2, that's 2 over 7 times x squared, plus 0 plus 0 plus 0 plus 0 forever. So, what's the Taylor series for x squared plus 5x over 7? I'm sorry, I forgot the 2 there. 2x squared plus 5x plus 7. What's the Taylor series for 2x squared plus 5x over 7? What?
Why did you put a 2?
I don't know. Why did I put a 2 here?
This is the second derivative.
Okay. Something doesn't seem right though.
This is the second derivative. It's 2 times.
Yeah.
That's right.
The first derivative brings the 2 down from
Yep. Something's not right. Because look what we have on the left-hand side. We have x squared plus 5x over 7. And on the right we have 2x squared plus 5x over 7. Are those equal?
the.
No.
Something's off there, first derivative.
Oh, I know what the mistake is. This should be divided by 1 factorial, and this one gets divided by 2 factorial. What's 2 factorial? 2, so that 2 and that 2 cancel out. And we proved that x squared plus 5 over 7 is equal to x squared plus 5 over 7. Do you believe it?
I do now.
I do now. So, you gave me a polynomial for your function. What's the Taylor series for a polynomial always going to be?
Same thing.
The same thing. It will always be the polynomial. Okay. So, not a bad choice, but not a very interesting one. Give me a more interesting function. Which one? ln x. Where do you want to center it?
1.
At x equals 1. At c equals 1. We can't center that one at 0, can we? Unfortunately. Okay, so what we need is we need a table. We need f at 1, f prime at 1, f double prime at 1, f triple prime at 1, and maybe we'll have to go all the way to the 4th derivative. What do I get when I plug in 1? What's ln of 1? 0. What do I get when I take the derivative? What's the derivative of ln x? 1 over x. So I plug in 1, I get 1. Think of 1 over x as being x to the negative 1. What's your second derivative?
Negative x to negative 2.
And you plug in 1 to that, you get
Negative 1.
negative 1. Third derivative is?
1.
Not 1,
So
not 0.
that's the -3.
2x to the -3. So when I plug 1 into that, I get
2.
2. What's my fourth derivative? -6x to the -4. So when I plug 6 into that, I get, or when I plug 1 into that, I get -6. Are you seeing a pattern in those numbers yet? Well, I see one pattern. I see that it goes positive, negative, positive, negative. It's alternating. Do you see a pattern in 1126? That's 0 factorial, 1 factorial, 2 factorial, 3 factorial. The next one's going to be 24, because again, you're going to pull the exponent down. So the next one would be a 4 factorial. So we are definitely getting factorials. All right, so ln x is equal to, well, the first one was 0. I'll write it down, 0. Plus, then I had 1 times x minus 1 divided by 0 factorial.
Where's the x minus 1?
We're centering at c equals 1.
Oh, okay.
The next one is minus a 1. X minus 1 squared over 1 factorial. Plus, the next one is 2 times x minus 1 cubed divided by, no, something's not right there.
The power is supposed to match up with the factorial.
The power should match up with the factorial. So this one is this one down here is 1 factorial. And then this one is 2 factorial, this one is 3 factorial. The factorials match the powers. These numbers are just my coefficients. 1, 1, 2, okay. Then the next one would be minus 6 times x minus 1 to the 4th over 4 factorial, plus, and it would continue on and on and on forever. What's 1 divided by 1? What's 1 divided by 2 factorial? 1/2. What's factorial? 1/3. What's 6 divided by 4 factorial? 1/4. What's the next one going to be? 1/5. So this is the sum from n equals 1 to infinity. I have x minus 1 to the n divided by n. Right? Because when I plug in 1, I get power 1 divided by 1 factor, divided by the number 1. When I plug in 2, I get x squared and a 2 on bottom. When I plug in 3, I get power 3, a 3 on bottom. But then I need to remember that this is alternating. So I need a -1 raised to what power? I think I need a n plus 1. Why n plus 1? Why not just n? Because the first one started positive, didn't it? So if I plug in 1, that would give me 1 plus 1, which is 2. -1 squared would give me a positive number. And then when I plug in 2, 2 plus 1 would be 3. -1 to the 3 would give me the negative. So there's the power series for ln. Any other interesting functions you know? E. Nick, did you have a question?
If we graph that, is it mostly the graph development?
That's a good question. Y equals, we'll graph ln x, and then we'll graph x minus 1 minus x minus 1 squared divided by 2 plus x minus 1 cubed divided by 3 plus, nope, minus x minus 1 to the 4th over 4. Is that enough terms, you think? Divided by 3, because we have this 2 on top. That 2 reduces with the 2. That 6 reduces with 3 times 2 times 1, so the only thing that lives is the 4. So there's ln x. There's my polynomial. Does it look like ln x?
For that period of time between 1 and 4, it's alright.
It looks pretty good. Let's zoom in a little bit here. Here's ln x. Looks pretty good between maybe 0 and there's 1. 0 and somewhere over there. Looks pretty good. How could I make it look better? Add more terms. But the reality is, what's the radius of convergence of that series? Well, I think you could go ahead and do the ratio test, and from the ratio test you could show that that series only converges between 0 and 2. So, to say that this looked good between 0 and almost 2 isn't bad, considering we only did 4 terms of the Taylor polynomial. And it still looked pretty close.
In our calculator, can we plug it in as a sum for y2? And then just change the top term, take it farther? Can we put that whole thing in there?
That's an interesting thought. I never tried that.
So you can math sum.
Yeah, I wonder if you can go math.
It'll come up, I just don't know how to do it. Like you're going to have two, you're going to have like a y and an x.
Where's that sum? There it is. It's under here somewhere, isn't it?
0.
Mine's in math. If you like press up,
I just try reading out onto my
press
computer.
up, up, that was mine.
Here. You need mine as well.
I know, it's under stat on mine.
Oh yeah, mine.
There it is. What you have to do, oops, I gotta go back to y equals. I don't know if this will work or not. You need to tell it you want to sum the sequence of x minus 1 to the n, comma, oops, got my alpha lock on. We want it to start at 1, end at, we got to end it somewhere where the calculator won't go to infinity.
30.
Let's try 6. Got to go by ones. I think I'm missing something. Yeah. I know what I'm missing. You got to tell it what the variable is. All right, so I don't know if this is going to work or not because I don't know if this sequence routine in the calculator allows me to have an x there or not. Let's try 6. 6 minus 1 to the 4th but we'll find out. So we want to sum the sequence of x minus 1 to the n from n equals 1 to 6. All right, so it looks like it did it. It looks like it gave us some sort of 6th degree polynomial. And again, what I think we can see is it's matching decently right around the number 1. But then once you get past 2 and once you get past 0, it diverges badly. The radius of convergence is only between 0 and 2. And let's try the 11th degree polynomial. See how long it takes the calculator to do all that arithmetic.
The first one looked different than mine.
What did it?
Yeah, mine looked more like what we did with the individual.
I don't think you're dividing by n.
Oh, I forgot to divide by n. You're absolutely right.
Yeah.
And I needed to alternate. Wow. I forgot a lot of stuff, didn't I?
The primary is okay.
Now let's see the calculator think. Exciting, isn't it? Oh, they're just drawing something. Okay, so but what you can see is between 0 and 2, it looked like it converged very closely. Looked like they were very similar. And then it blew up.
It doesn't matter what we put in, it's only going to run a hash for that time.
That's exactly right. Because you could use the ratio test and you could show that this series only converges absolutely between 0 and 2. Which makes sense because we centered it at 1. Can I go any further to the left than the number 0? No, because ln is not defined for any number 0 or smaller, is it? So the furthest I can go from the left is 1, which means the furthest to the right I can go is 1.
Is there any way to center at like all numbers at the same time?
Unfortunately, no. For ln, there is no way to write a power series for ln that will converge for all real numbers. Because, let's say I centered it at 106. What's the furthest to the left it could go if I centered it at 106? 106, because once I hit ln of 0 is undefined. So even if I centered it at c equals 106, the best possible thing I could hope for would be my radius of convergence would be 106.
What if we centered it at infinity?
I'm not quite sure how you take x minus infinity. I don't think that would work. All right, in your book here, they give a list of some of the famous power series. ln, hey, we just figured out that one. There it is. Probably the most famous ones, the ones that are used the most, are e to the x, sine, and cosine. And you should notice that e to the x, sine and cosine are pretty related. Notice that e to the x has 1, then it's got an x squared over 2 factorial, x cubed over 3 factorial, x to the fourth over 4 factorial, so on and so forth. How is sine similar to that?
It's the odds.
It's got all the odds plus it alternates. And how's cosine similar to e? Has all the even powers, and it also alternates. So there's a very strong relationship between sine, cosine, and e. This is a famous one. 1 plus x to the k. Anybody know what that's called? When you take 1 plus x and you raise it to a power? Like, what do you do? Like, you know how to do 1 plus x whole thing squared, right? How do you do 1 plus x squared? You just FOIL it out. What if I gave you 1 plus x cubed? Triple FOIL. What if I gave you 1 plus x to the 5th? Cry? You can start using Pascal's triangle. What's Pascal's triangle? How are you getting those numbers? You always have a 1 on the diagonal, and then you add 1 and 3 makes 4, 3 and 3 makes 3 and 1 makes, and then another 1. So if you wanted to do to the, what power did I say, 5th power? There it is. You would have 1 plus x to the 5th would have a 1, then it would have 5x to the 4th, 10x cubed, 10x squared, 5, oops. My x's should be going up in powers. 1, 2, 3, 4, 5. What if I wanted to do x plus 1 to the 100? That'd be a big triangle, but could you do it? Yeah. In theory. There's also a famous binomial expansion for that. However, Pascal's triangle doesn't do you any good if that power is, say, a 1/2. What's 1 plus x raised to the 1/2?
The square root of that.
It would be the square root of that. But if you want, you can write that as a series, where k would be the number 1/2. So you would have 1 plus 1/2 x, then you'd have 1/2 times negative 1/2, 1/2 times negative 1/2 times negative 3/2, 1/2 times negative 1/2 times negative 3/2 times negative 5/2, so on and so forth. So you could get a power series expansion for the square root of 1 plus x.
So it only works when it's 1 plus x. It wouldn't work if it's 2 plus x or 1 minus x.
1 minus x is easy to fix. 2 plus x is fixable, but a little harder. Good question.
Get it in the form. 1 plus x. Is that what you're saying?
So let's answer both of his questions. His first question was, we have a power series for 1 plus x to the k. I'll just write down the first couple terms. It's 1 plus kx plus k times k minus 1 x squared over 2 factorial plus k times k minus 1 times k minus 2 x cubed over 3 factorial plus so on and so forth. What if I wanted 1 minus x to the k?
Negative, then subtracting it, and the k would be k plus 1.
Nope, but you're on the right track. How about if I wrote this as 1 minus negative x to the k?
Get rid of the 1.
Everywhere I see an x, I'm not going to write x, I'm going to write negative x. So that would be 1 minus kx. Well, what happens when I take negative x and I square it? It becomes positive again, doesn't it? So the next one would be k times k minus 1 x squared over 2 factorial plus negative x cubed would make it a negative k minus 1, k minus 2 over 3 factorial x cubed, so on and so forth. So x plus k gives me one series, x minus k gives me the exact same series except it's alternating. It's going to be the alternating. What if you want 2 plus x to the k? Well, you write it as 1 plus x all to the k. And then you go back up to this series up here. Everywhere you see the letter x, you don't write the letter x anymore, you write 1 plus x. Okay?
So that middle one would be 1 plus negative x?
Yeah, that's the other thing, right?
Yep. 1 plus negative x. Okay? So that's a very common technique. Generally, to find power series, we try to avoid deriving them. What we try to do is take a power series that we already know, write this in the form of that power series, and then plug things in. And we'll do some more of that on Monday. Anyway, a couple more interesting power series that they've derived for us. How do you find the power series for, well, they give me arctangent. That's not the one I thought. I was looking for the power series for tangent. They give us arctangent. Arctangent's kind of interesting. It's got odd powers divided by odd coefficients. And then there's one for arcsine, which has lots of bizarre stuff. 2 to the n over n factorial, whole thing squared. Not quite sure how they figured that one out. Not very nice. Okay, like I say, the 3 big ones, the 3 that we will use the most are e, sine, and cosine. Those are the ones you should be familiar with.
Is there a close relationship with y and hyperbolics?
Is there a close relation for hyperbolics? Yes, there's a very close relation for hyperbolics. That's not given in this book. But the power series for hyperbolic sine turns out to be x plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7 over 7 factorial. How's that related to the regular old sine function?
It's the same, but not alternating.
It's the same but not alternating. And the same thing works for hyperbolic cosine. Power series for hyperbolic cosine happens to be the same as regular old cosine, except it's not alternating. So what does that tell you about hyperbolic sine plus hyperbolic cosine? It's e to the x. How come? Because you'd have 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. That's the power series for e to the x. Hyperbolic sine plus hyperbolic cosine is exactly equal to e to the x.